Okay, good morning. Let's continue our discussion on chapter 2. We'll get into node voltage analysis today. And well, probably not mesh current. We don't have enough time. Let's bring up new share in section 04. Let me stop here, current division. So let's pick up node voltages and mesh currents. So these are the last two major analysis techniques that's left in chapter 2. There's still a long way to go. We're not even halfway there yet. Okay, but these are the last two techniques. And both of these techniques build on the techniques that we have learned previously. So Ohm's law, KCL, KVL. If you have taken a look at the final exam page on Canvas, if you have not done so yet, I would urge you to check it out. It's been there since the first day of class. This is a guaranteed problem in the final. Okay, the final exam again lists the dates and the times and the options for students, and it also lists the topics of assessment. So node voltage analysis, mesh current analysis, guaranteed problem in the final exam. Very important topics. Okay, so since I'm introducing the topic of node voltage analysis today, I also expect to cover the explanation, the theory, as well as one example problem. So when a topic is introduced in class, students are expected to open up that homework and take a look at it. Once I finish covering the topic in class, I will again announce it, and I will say that the topic is not concluded. The homework is assigned at the beginning of the introduction, and then the due date will be updated right after the topic is finished and covered in class. Okay, so node voltage analysis, we are introducing the topic today, and I will finish it up within the next 50 minutes. All right, so let's get on it. Before we begin the analysis technique, there are a few things that we need to note. Node voltages and mesh currents. We will talk about mesh currents when we get to mesh current analysis. So ignore IA and IB as far as this illustration goes. Okay, we are not looking at IA and IB. We are only looking at the nodes, the node voltages, and the node voltage analysis technique. So what do we know of nodes? A node in an electrical circuit is a junction of two or more components. So the first thing we do is identify all the nodes in the circuit. Okay, in this case, it is already given to us A, B, C, and D. Okay, the four nodes in the circuit, meaning the four junctions in the circuit, are given to us A, B, C, and D. If you look at the bottom node, it extends all the way from here to here. All these connections is one single node. Again, it's a wire. The wire can be long, it can be short. It doesn't matter how long or short it is. If it's the same electrical junction, then it is a node. It is one single node. It is not three, it is not two, it's one single node. That's good so far. Okay. Then, if you look at each one of these nodes, sorry, not nodes. If you look at each one of these components, R1, R2, R3 is not noted here. I'll note it right now. And then R4. Four resistors in the circuit. Each one of them have currents flowing through them and have a corresponding or proportional voltage drop. That voltage drop is marked and noted as V1, V2, V3, and V4. The polarities of all four of them are noted. Okay. Those are assumptions that we would make at the beginning of our analysis. In this case, in this illustration, they're already provided to us. Okay, they're already provided to us. V1 has a polarity of plus and minus on the left. V3 has a plus and minus as shown, again, left and right. Node C has multiple signs. So do not be confused. Those signs do not have anything to do with the voltage at C. Okay, those signs refer to the resistor voltages, not to the node voltages. So a question always comes up is how come node, one single node has a plus and a minus sign? Well, that has all to do with the reference. In this case, those signs are simply noting the polarity of the voltages of those resistors, nothing else. All right, so let's begin. We see that voltage source Vs is connected between nodes A and B, right? Connected between A and B. So I can express that source voltage Vs in terms of the node voltages at B and A. And because there is a plus here and a minus here, I can say VB is at a higher level than A. And so I can write VB minus VA. Okay, VA. Now, in node voltage analysis, we always want to choose a reference node. And by that I mean is the second subscript of a two subscript notation. Voltages are nothing but the difference in electric potential between 2 points, right? We are measuring the voltage at one point with my reference at another point. So the second subscript is always the reference. So in node voltage analysis, we always want to choose a reference node. And that reference node is common to all other nodes, meaning all other voltages are measured with reference to that node. Hence, it is known as the reference node. So A is chosen as a reference. And if A is chosen as reference, what is the voltage at A measured with reference to itself? 0 volts. So automatically, I have the answer for one node. Okay, automatically I have the answer for one node. Keep in mind, and this is an important point, when you begin your analysis, you can choose any node you want as your reference node. Any node. You could choose B, C, or D in this case. Was there a question? Okay. So as I said, you could choose any node you want as your reference. Your answer will still end up being correct. It doesn't matter whether you choose A or B or C or D. If you choose B, VB is equal to 0. If you choose C, VC is equal to 0, and D, VD is equal to 0. It doesn't make a difference. But if you have a voltage source in the circuit, like we have here, then it makes things easier. It makes things easier if you choose one end of that voltage source as your reference, because it automatically gives you a value for the other terminal. So if I choose C as my reference node, I can write VB minus VA is equal to whatever VS. If I choose A as my reference, as I've done here, if A is my reference, I can automatically write voltage VB is equal to the supply voltage Vs. Does that make sense to everyone? And you can do this mathematically also. Since VA is equal to 0, if I plug in 0 volts in that equation, I get VB is equal to Vs. How about if I choose B as my reference? If B is reference, then VB is equal to 0 volts. And in that case, my equation would become Vs is equal to 0 minus VA, and therefore VA is equal to minus Vs. It's simply because this B is my reference, B becomes 0 volts, But that doesn't change the fact that node A is at a minus with reference to B, lower potential than B. And so VA with reference to VB would be minus of VS. The magnitude remains the same, but the level, level and the magnitude remains the same, but my sign changes to indicate which is my reference node. So this just proves it mathematically. Conceptually, if the positive end of the voltage source is taken as reference, then the other node is minus. Let's take a 10-second pause. Let me know if anyone has any questions. Does that make sense to everyone? Again, the easiest and the most efficient thing to do is to use the negative end of the voltage source as your reference. And so you automatically have a positive value at the other end of the other node. So now, remember I said, actually I haven't said it yet. I'll say, no, let's wait on that. I'll come back to that point again. Let's continue with this. So I said VS is connected between VA and VB. VA is my reference, meaning B is higher. So I would write VB minus VA. Now I can express each one of these resistor voltages, V1, V2, V3, and V4, in terms of those node voltages. And here's where that polarity comes into the picture. Polarity for V1 indicates that B is higher than C. And so when I write the equation for V1, I would say it's VB minus VC. Okay. The voltage polarity for V1 is plus on the left, minus on the right, meaning VB is higher than VC. And so when I express V1 in terms of the node voltages, I write it as V1 is equal to VB minus VC and not VC minus VB. And so on and so forth for all the other resistors in the circuit, V2, V3, and V4. Does that make sense? Okay. We are expressing each resistor voltage in terms of the node voltages. Okay, in terms of the node voltages. Node voltages do not have a two subscript notation because the second subscript is implied. So VB is simply the same as saying VBA. Because A is 0, the second subscript is simply implied. So when you're talking about node voltages, it's always with respect to the reference node. The reference node is automatically 0. So VB is VBA. VC is VCA, VD is VDA. So there is no two subscript notation for node voltages. All right, any questions? Let's move on to the next part. What we do for node voltage analysis is we want to write out equations, right? Generally speaking, math, if you have one unknown variable, you need at least one equation to solve for that unknown variable. If you have two unknown variables, you'd want two equations to solve for those variables. If you have three, you want three equations, and so on and so forth, right? In node voltage analysis technique, our unknown variables are the node voltages. And so we wish to write equations for those unknown node voltages. And the technique we use to write equations is KCL, Kirchhoff's current law. Node voltage analysis requires current law. Okay, current law. And again, it will make more sense when we get to an example. But for now, we look at this one right here at the top. resistor R with the current going from left to right. And VA and VB are already noted. So which end is plus and which is minus? Current going from left to right, current always goes from high to low. So point of entry is always plus and point of exit is minus. So VA is plus, VB is minus. So again, in this case, the current direction for I is given to us, but this would be an assumption on our part. Okay, this would be an assumption on our part. So point of entry is plus, point of exit is minus. So I can write current I in terms of, I'm going to say VR is the resistor voltage. Ohm's law gives me I is equal to VR over R. Then I would express VR in terms of the node voltages. The resistor voltage VR is VA minus VB. Current I direction is an assumption, but that assumption gives me VR as plus on the left, meaning A is higher than B, and so I is equal to VA minus VB divided by R. So these are the two steps that we will use. Okay, you express the resistor voltage in terms of the node voltages. You guys with me so far? Yes. Okay. Oh, I thought you had a question. Okay. All right. Thank you. So then we take that and we apply to the example below. Larger example below, we have 3 resistors and 4 nodes, A, B, C, D. We are not concerned with the reference node just yet. Okay. This is just an example or an illustration to show how you would apply KCL to generate an equation. So in this case, I have current directions given to me, so I'm going to quickly mark out the voltage polarities. And I will note this as VR1, VR3, and VR2. If I apply KCL at node B, I would obtain the equation I1 equals I2 plus I3. I1 equals I2 plus I3. Then the next step is, so first step is KCL. Next step is Ohm's law. From Ohm's law, I get VR1 divided by R1 is equal to VR2 divided by R2 is equal to VR3 divided by R3. Ohm's law. And then finally, you would express each resistor voltage in terms of the node voltages. And so I would have VA minus VB divided by R1. VR2 is the difference between VB and VC. And so I would write VB minus VC over R2. And VR3 is between B and D. So I can write VR3 is VB minus VD over R3. Let's take a 10-second pause. Think over this. Let me know if you have any questions. The expression of the resistor voltages in terms of the node voltages comes from the fact that the voltage polarity is established, and the voltage polarity is established due to the direction of the current that we assume at the beginning of analysis. Again, at the beginning of our analysis, we assume I1 going from A to B. If it goes from A to B, automatically it follows that A is higher than B, meaning A is plus, B is minus. And so when I write the equation, it becomes VA minus VB. If I were to choose I1 going in the opposite direction from right to left, then it would be VB minus VA. Does that make sense to everyone?
Could you repeat that?
So our direction for the current for I1 goes from left to right in the figure here. And because it is going from left to right, A is higher than B. That means VA is higher than VB. So when I write the equation, it becomes VA minus VB. Since I1 is going from A to B, it is VA minus VB. If I1 was going from B to A, it would be VB minus VA. Depends on what direction we choose at the beginning of our analysis. Okay, any other questions? So at this point, we have unknown variables, VA, VB, VC, and VD, and our known quantities are R1, R2, and R3. 4 unknown variables, right? But let's go back one slide. We had a similar illustration right here, right? 4 nodes, A, B, C, D. If we choose A as the reference node, we have 4 nodes, so 4 unknown variables. But if we choose VA as the reference node, we have an answer for A. So VA is equal to 0. Then VB is connected to the other end of the power supply. So I know my answer for VB, which is VS. I'm left with only 2 unknowns. So I need to write only 2 equations. And that's why it is more efficient to choose one end of the power supply or one end of the voltage source as my reference node. It automatically takes out one unknown, one less equation to write. The point is, even if you choose C or D as your reference, you can still arrive at the right answer. It is just more work because you have to write more equations. So it's a slightly less efficient method. Okay. Is everybody clear on this? All right, so let's recap. First step, identify all the nodes, choose a reference node. The reference node is always 0 volts. Assign branch currents to branches, meaning the resistor currents. You assume the direction based on logic. Even if you choose an opposite direction, does not really matter, as we will see in the next example. You apply KCL at every node. Apply KCL at every node using the direction of the currents that we just assumed. Apply Ohm's law. Sometimes it's easy to skip the step. I would strongly recommend do not skip the step. Write it out so that your chances of making an error are reduced. Okay. And then finally, express each resistor voltage in terms of the node voltages. These node voltages are the unknown variables in our equations. You solve for those equations with any method you want. Okay. All right. Do the steps make sense? And you can have these steps listed out in your equation sheet. But when you need to work fast and efficiently, you need to be able to remember how to apply it. Okay, let's look at the example. Solve for all branch currents and node voltages. All branch currents and node voltages. I particularly like this example because it shows actually that it doesn't matter which direction you choose the current flowing through. Okay, it simply gives you an answer based on the analysis, assumptions that we make at the beginning of the problem. All right, so what is given to us? In this circuit, we have 4 resistors and we have 2 current sources. Values for both current sources are given to us, 10 milliamps and 50 milliamps, and resistor values are all given to us too. What is the first thing we notice? Relationship between R2 and R3. What can we say about that relationship? They are in parallel. Both have 2 terminals and both of their terminals are connected to each other. And so R2 and R3 are in parallel. I'm going to note them as R23 and R23 would have a value of 1 over 2000 plus 1 over 10,000. So what is the answer to this? I think it is 1,666.667 ohms. So even before actually applying node voltage analysis, we have reduced that circuit. Now, next step is to identify all the nodes in the circuit. So how many nodes do we see? Your options are 3, 4, 5, 6. No penalty for like wrong guesses or wrong answers. So take a guess. 6? Anyone for 6? How about 5? Do I have 5? Okay. Anyone online? How about 4? Going once, going twice. Let's look at this. Current source, 1 drag, wire going to R3, wire going to R2, wire going to R1. Doesn't matter how many dots or connections we have, as long as there's wire going around, it is the same node. Same thing here, and same thing at the bottom. So there's only 3 nodes in the circuit. Take a 10-second pause, think over it. Let me know if it doesn't make sense. Yes. Sure. Sure. So ignore the ground symbol. That doesn't have anything to do with whether it's one node or not. But the connection is, it's a wire that goes and makes a connection with the other components, and the same wire. As long as it's the same wire, it's the exact same node. The same electrical junction. Doesn't really matter whether it comes to a point or whether it's just drawn schematically different. We could draw the bottom node like this. Still 4 components. There's still 1 exact node. Okay, so I keep repeating this because students definitely have a hard time trying to identify nodes, right? This is the first step. And circuit schematics are something that can be drawn any which way. You could draw a circuit schematic on a side, upside down. There is no, in physical terms, if you're assembling this circuit on a lab bench, there is no top, there's no bottom, there's no left, there's no right. It's just the circuit schematic we see on paper or we see on the screen that makes it top, bottom, left, or right. Okay. So again, as long as is it the same wire that makes a connection to the different components, you can draw it out. Draw out the circuit in a way that makes sense to you. As long as there are only wires, then it's a node. Again, going back to the example of a extension cord, right? You could take 100 feet long extension cord, plug it into the wall, and you would still expect the other end to be live, right? So it's the exact same node as the wall outlet. Doesn't matter how long it is. And that's the point. So only 3 nodes in the entire circuit. And I can combine R2 and R3 together. So I'm going to redraw the circuit like this. This is R23. I have a resistor going here, another resistor going here, I have a current source, I2, current source I1, and the bottom node. Mark the top left node as A, top right node as B, and the entire bottom node as C. Current I1 is going up top, current I2 is coming down. And here's where it gets interesting. Which direction would you choose the current? Logically, I just like to follow the left to right convention. So if I'm starting from the left, my current is going in this direction. I would choose R23 to go from left to right. I would also choose IR4 and IR1 coming down from the top. So IR4 and IR1. Again, as I said, the assumptions can be anything. Okay, going in one direction, going in the opposite direction will not make a difference. 10 students can choose 10 different things. One student could choose the opposite direction for R23, another might choose opposite for IR1, for IR4, could make a different assumption about the reference node. It doesn't really matter. You could solve this problem with different assumptions and still end up with the same answer. So going down for IR1 and IR4, and then going from left to right for IR23. So then we assign the polarity due to these assumptions of the direction of the current. Point of entry is plus, meaning the voltage across R23 is plus on the left, minus on the right. And for IR1, or for resistor R1, is like this, coming from top, so it's plus and minus. Now, anytime I solve an example in class, I tend to use the component notation as the subscript. So IR1 simply refers to the current for R1. VR1 is not labeled here on the schematic, but VR1, students should understand, it refers to the voltage for the resistor R1. Make sense? Right? So this is VR1. This is VR23. And this plus minus, a little difficult, getting crowded in here, but it refers to VR4. Okay? So anytime I talk about subscripts, that is what I mean. I'm referring to those components. So how many unknowns do I have? 2. VA and VB. Let's take a 10-second pause. I want to make sure everybody understands the setup of the circuit. Setup of the analysis. Everyone good so far? Any questions? Okay, this is just a setup. Okay, initial setup. We assume the direction of the currents, and because we assume the directions as shown in the circuit, we can then make an assumption and mark the voltage polarities for each resistor. And from that, I can write out my equations. I'm going to choose C as my reference, and therefore VC is automatically 0. You could choose VA, you could choose node A or node B as your reference, And then in those cases, VA or VB would be equal to 0, respectively. Okay, since I chose C as my reference, VC is equal to 0. Then the next step is to apply KCL at node A and B. At nodes A and B. Okay, KCL at A gives me I1, the current source I1 entering the junction, and then two currents, IR1 and IR23 leaving the junction. So KCL at node A gives me I1 equals IR1 plus IR23. I1, of course, is fixed. I can't do anything about that because the value is given to me. But I would take IR1 and express it using Ohm's law as VR1 divided by R1 plus VR23 divided by the resistor R23. That's the second step of applying Ohm's law. And then the third step is, of course, expressing each resistor voltage in terms of the node voltages. I'll wait until students catch up. So at this point, I would express VR1 as node voltages. I would also plug in the values. I1 is given to me as 10 milliamps. So it's 0.01. VR1 is VA minus VA minus VC. And R1 is 1000. Plus VR23 is VA minus VB divided by R23, which is 1666.667. VC is 0 volts. It's a reference node. And typically from this point on, what I do is I eliminate the numerator. That's how I like to solve it. You can choose whichever technique you are comfortable with. So I multiply everything by 1000. That gives me 10 is equal to VA plus this becomes, let's see, what do I have? 1000 divided by 666.667. My notes are somewhere in my office and I haven't been able to locate them yet. Just too many boxes and stuff. So this becomes 0.5999. Now, I've been taking 4 decimal places just because it's force of habit for me. But I don't expect students to do the same, right? Students can just follow along whatever they're using. Like you can do 2 decimal places, and if you round this up, it goes to like 0.6. But what I do is I'm doing this. 0.599 VA minus VB. Okay. It's just force of habit for me, since I've been doing this for more than 3 decades. I always like to take as many decimal places as I can so that my error, chances of errors are reduced. So this becomes, what does it become? I would rearrange the terms and I would have 1.5999 or 1.6 if you prefer, minus VB is equal to 10. And I'll call this as my equation 1. Okay, equation 1. Does that make sense to everyone? Let's take a 10-second pause.
Can I ask you a quick question, Professor?
Uh, just hold on. There's a question in class, and I'll get to you in just a second, in a moment. Yes, you were saying? Yes. So this step, all I'm doing at this step, yeah, VC is reference, so that's 0 volts, and then I'm times 1,000. That's all I'm doing to reduce that equation. Okay. Someone had a question online. Go ahead, please.
It was the same question, so I'm good now.
Okay. All right. Yeah. So I tend not to skip steps, but I think we were running out of time, and that's why I ended up skipping that step. But again, as I said, it's at this point, once you have your unknown variables, it's a form of an algebraic equation, which is x plus y equals, ax plus by is equals c, and that's the standard format that we're going for here. So if students have a other preferred method, they'll solve by creating a matrix and solving it that way. That is absolutely fine. Lots of students like to do that. And so at this point, again, as I said, I don't force my techniques on students. This is something we learn in school, middle school, right? That's when we start. Yeah. No, these equations. Anyway, this is something I think we learn in what is the equivalent of a middle school. And so, it's years before, it's years since students have been learning this technique. And so I don't try to change them. That's what I'm trying to get at. If students are familiar with the technique of applying math at this point, then you can stick with that technique. Okay, so let's then apply KCL at the other node. So if I KCL at, what was the other node? B. At B, I would get, what do I have? IR1, sorry, not IR1. IR23 is entering the junction, and IR4 and I2 are leaving the junction. So I would say IR23 is equal to IR4 plus I2, and IR23 I can express using Ohm's law as VR23 divided by R23, and this is VR4 divided by R4 plus I2. VR23 is still VA minus VB divided by R23. VR4 is VB minus VC divided by R4. VB minus VC, yes, plus I2. VC is equal to 0 volts. When I plug in the resistor values, I get VA minus VB divided by, and this would be equal to VB divided by, what is R4? 2000 plus I2 is 50 milliamps, so 0.05. Now I'm going to multiply everything by 2000. And that gives me, what does it give me? By 1.1999. And again, students can simply round up 1.2. I'm going to take 9 VA minus VB equals VB plus 100. You reduce and rearrange the terms, you would get VA minus 2.199 VB equals 100. At this point, I have my two equations for two unknowns. two unknown variables, VA and VB. I have my two equations. You solve them using any method you're comfortable with. If you have a programmable calculator, you can plug these equations in there. It will spit out a couple of values for you. Okay. But you need to be adept at using your calculators. My calculator device is from the 90s. Okay. It's not fancy. It cannot do any programmable functions. So I solve it manually by hand. Did you have a question? Yeah. No. So these unknown node voltage analysis is for solving node voltages. Once we have those node voltages, then we can solve anything in the circuit. Okay. So again, when we solved this, we obtained, what did we obtain? And well, if you are online or if you're in class, if you have a calculator, go ahead and solve these. And I think we get VA is minus 13.569 volts. And VB is minus 52.857 volts. Very interesting numbers. So what does it mean? I'll take a 10-second pause while you write it down, think over it. Any questions at all? We obtain negative answers, okay, negative numbers. Doesn't mean that your answer is wrong. This voltage at A and B is measured with reference to C. So think about what this means. A, B, and C. A is 0 volts, right? I'm sorry, not A. C is at 0 volts, right? It seems C is the highest point because all the other numbers turned out to be negative. So if C is at 0 volts, it simply means A is below C, is minus 13. So A is 13.5 volts below sea level. It's underwater. And B is even further down. Of course, not to scale, but B is at minus 52.857. Does this make sense to everyone? That's all it means. It doesn't mean anything else. If at the beginning of our analysis, we chose A as a reference, what would be our answers? So I'm going to mark out here. If A is reference, then VA is equal to 0. What would be VC? Plus 13.5. The answer doesn't change. And then VB would be the difference between 13.5 and 52.8. So VB would be equal to VB minus VA. And if B was your reference, then both VA and VC would be positive. Make sense? One final point. Once you have these node voltages, you plug it back in there. You plug it back in these equations. VR1 is VA minus VC. Now you have the answer for VA. You plug it into that equation. You get the answer for the voltage across R1. You plug it back into the equation for VR23. VA minus VB gives you VR23. So you now have your resistor voltages. Once you have resistor voltages, you can find IR1 and you can find IR23 by Ohm's law. And that's how we can solve for any unknown voltages and currents in the circuit using node voltage analysis. Okay, we'll stop right here. Consider the homework for node voltage analysis as assigned. Again, we introduced the topic today and well, went over time by a couple of minutes. We ended up covering it also. So if you have any questions, you get in touch with me. But the homework for this would be due, I want to say today is Wednesday, Thursday, Friday, Saturday is like 3.5 days. Maybe I might do it till Sunday. I don't know yet. But either expected either Saturday or Sunday. Okay. And I will adjust the due dates on the website. All right. Thank you very much. We'll end class here today and I will see you all on Friday.